instruments. So, that was right. Yeah.
Oh, ще раз.
Okay. Company, supply, but we try not only to buy, not only sell instruments, but support user installation, service support during warranty and after warranty security. Also, we support chronology of life. At this moment, we are on the market more than 20 years.
Презентер. Ні, це просто.
So, at this moment we represent three instruments. It's American company, world leader in manufacturing system for thermal analysis, rheology, mechanical analysis, and micropolarimetry. This company was started as a part of the one company. And now it's a part of Waters Corporation. The next company is micropolarimetry. Sorry, it's okay, but I will stop quite much. But it's not completely enough.
Just a moment, please. Я душу писал, це встигаю. Я розумію, просто не буду.
Okay. Next,
Everything to bring attention to the personal page.
Copy is nice attention. The next company is Microanalytics. Its company provides world-leading technology for characterization of particles, powders, and porous materials. It helps to understand the porosimetry, particle size, gas absorption, chemabsorption, other. Lightnova company. Lightnova company is company in Denmark. It's not just a whole company as well, but the company is Ukrainian soul because CEO and biggest part of CEO is analyzed from Ukraine. So they suggested the new technology of Raman, the Raman microscopes and Raman spectrometers. Our new partner is RE Solutions. They suggested big integrated thermograph systems for non-destructive analysis. And also it's physical electronics. Company is an American company and suggested material surface and they sell such instruments like X-ray, photoelectron spectroscopy, system for organoelectron spectroscopy, and mass iron mass spectrometry. Today, as the topic of conference is refractory materials, we will speak about systems from each company that can be used for analysis of refractory compounds, but also for transcription, as we found the most popular topic.
Здесь писав про це?
No. let's start from instruments, from the instruments, and first instrument, I think it's very important for analysis of refractory materials is gelatin. The instruments suggested big number of gelatometers, but all of them provide information about the near thermal expansion coefficient, about the sintering processes, about shrinkage and soldering points. There are different types of instruments. The easiest and the most popular is horizontal gelatometer. And they work from minus from temperature of the liquid nitrogen, yes, and till 1000 and 700 degrees. And they can work in vacuum, air, and gas atmosphere. For sintering processes, more useful is because the gelatometers they work in a wide temperature range and provide more information during the process of sintering in different colors. Also, the instrument suggested optical gelatometers. If you work with small samples, with thin samples, it's important not to distract the sample, so it's easy to use optical system. And also, the instrument suggested optical gelatometry platform. It can be used. It works in different modes. For the first, it's a heating microscope mode, horizontal gelatometer mode, and also in mode of proximity. Next type of instruments can be used for refractory compounds is the parametric analyzers. They use for research of the thermal stability, of genetics, of also for detection of moisture and electric content. They suggested different types of these analyzers. For refractory compounds, it's better to use simultaneous thermal analyzer because it works till 1000 degrees and the standard thermochemical analyzer works only depends on model only for 1000 or 1200 degrees. So all systems work with in inert gas and air, and all can be use special model for analysis in different atmospheres in a mixture of gases. Also, the instrument suggested systems which work in high pressure, and depends of your task, it can be or discovery of high pressure thermochemical analyzer or detect. Also, there are specific accessories for these systems. You can connect the mass spectrometer or infrared spectrometer for the thermochemical analyzer, and it helps you to detect lead gases in your sample during heating. So also there are special adapted kit, yes, if you go to dangerous material. Also, the instrument suggests big number of thermal analyzers for thermal conductivity and thermal diffusivity. For refractory compounds, it's nice systems. It's serious for serious discovery. It's not fresh and you discover the lesson. Mechanical tests. Here the instrument suggests not just only testing, but also the analysis and for analysis, detection of faculty life. There are different types of instruments. This is dynamic mechanical analyzer and of course, series has a big number of different models and for chemical analysis. Our hydrometric instruments, hydrometric is interesting for factory compound, which is particle size analysis. And this one was analyzer state graph. It's inorganic particle size distribution by X-ray segmentation. Also, interesting instrument can be a plastic holder for the detection of true density and different types of density.
I'll be fine.
Yes, I think it's most popular model. And there are three different instruments for analysis of surface area. It's Gemini, Crystal, and Reflex. They have different modes, so it's you choose instrument depends on the task. And you words about X-ray computer tomography systems. It's nice decision for non-destructive analysis. Not only of small samples, but from for analysis of parts from big samples. There are three types of systems that can be used for small or medium-sized parts. EasyDrum can be it's a small period for system that can be used with different accessories, and also EasyDrum is a big system. It's commonly used for day-to-day analysis. And surface analysis. Examples that can be what systems can be good for this on physical electronics. So like example, that's the most popular is Genesis system for non-destructive X-ray analysis. It's small part of information about our instruments. We are here during this conference. Please come to us and ask. We will be glad to discuss everything in details. Any questions?
Thank you.
Materials and our responsible in Ukraine for the presentation and for supporting the SAMSONOV conference. We greatly appreciate your contribution to the conference and your support of the material science community center. We will now have a 20-minute coffee break. We look forward to seeing you back at 11:40 for the continuation of the conference program. Enjoy your break.
Кава брейк в кімнаті поруч.
Ти будеш тут зараз?
Тут.
Я тоді прийду підміню тебе, добре?
Добре.
Добре. Наглянеш за сертифікатами і сумкою і все.
Добре.
А флешечка у вас, так?
Так. Це ваше ж? Зараз я йду.
Щось не вистачає.
А я думаю, це можна витягнути. Я працюю. Не вистачає на одному ноутбуці, воно трошечки
Я смотрю, у нас же обычно было.
напряг.
Ну, что-то людей. На первый. А вот сколько будет у четверг? Вы втроем, наверное, будете. Ты и Саша.
Побачимо, що буде.
Мой научение на бесплатное посылание на конференцию. Так, там меньше я буду і тут.
Телеграм ти є? А, ні, в цьому.
WhatsApp, Telegram.
Ну, я в Телеграмі, бо я просто розсилав його вже в Телеграмі, мені простіше перекинути туди просто. Тобі на коли? Сьогодні чи ти взагалі? Бо кожен день нове.
Сьогодні, вже створені на завтра, завтра.
Да, на всі дні.
Посилання на всі, бо я не знаю, чи завтра буде мати можливість мати. Накладки.
Наталья Євгенівна там, так що.
Зараз я знайду, отак от. Всі. Скопіювати.
Накладок немає.
Ну, у мене теж таке буває, що я за голову ловлюся. Так, я тобі в WhatsApp скидаю.
Стоп.
Бо я знаю, що ти точно тут в мене є. Воно, до речі, всі скинув. 25, 26. А, воно скриває. 28, є. Там і YouTube трансляція є.
А, я не чую, може, я питання не поспорю.
Вони це скинув. І так, як хочеш.
Знаю. Саша, так?
Вона мені просто нічого не казала. Так, що там вважати?
А то я щось не подивився. Розворотами своїми.
А що ми будемо битися з тобою? Вони сказали, що поліфі.
Вони замовили.
Джекі.
На дорогу сюди, да?
Пані Марковська попередила, що вона так.
А вона десь збіжала.
Вона тільки що вибігла.
Я думала, що це пані Маркуцька. Вона маленька, як є, вона ж була. Пані Маркуцька, це
Починаємо?
Ще її попередила, що це.
так.
Початок, так? This one is one small. We are opening the session. Low dimensional materials and nanostructures. Fractal analysis of well-confirmed results as medical quantitative evaluation of structure and depiction of properties. The field of Oscar presents here is for the research.
Бо якщо воно буде соя, або це. Можна оцей повісти зараз? Дозволіться.
Пані Марковська зараз вона.
Today I will present my work. That means a fractal analysis of the body joint zones as a method for quantitative assessment of structure and application of properties.
Презентером розкажи. Презентером.
So, traditional photographic analysis of body joints are primarily provides qualitative characterizations of microstructures and does not fail to full assessment of great boundary topology, preparation, or the heterogeneity of This is particularly important in
Вона буде
structure, or construction. Current trend and material science require the utilization of wealthy parameters reaching maximum complexity while simulating the structures on the quality of raw returns typically focus on the wealth metal. However, the heat effect metal is not less important, since it determines the strength, durability, and durability of the raw metal. That such works compared to inclusions in any parts of the world church and mention of its characteristic group and to make the structure only the selection of an appropriate growing form for human to the use of suitable material for temperature, speed, energy, temperature, or modifies the formation of units. So. Well, typical value Yes, well, должны быть фотографированы, для того, чтобы also the here, its structure and properties change other groups of be compared to those of the basement, cardias and radiants increase, especially near the wells, while impact soundless and corrosion resistance increase. The risk of results depends on welding that are welding stages and related to the feeder don't be small. While the results is it has been established that the heat effect zone refused several subfloors. Normalization motion. Complete representations of that diversification. Thus, supplements are labeled structural components with different parameters and geometry and conceptually different medical findings. This regard, it is proposed to apply fractal analysis as a method for quantitative assessment of value assurance flows. Using the non-void structural field, zero line as introduction and to evaluate its usefulness for predicting metal properties. While the model for the for the composition and characteristics of the material which evaluate additional structural components such as grains, conduits, grades, and their considers inclusions into other microstructural features. The magnitude of this work was two relations between the structure of characteristics and technical others of the value also known as the this method is based on the number of cells of different scales that cover the object on the side and make it possible to assess or showcase some characteristic of great objects. Fractal analysis was both with the derivation. In this work, was indicated the relationship between the fractal dimension of the range congress and the hardness in their corresponding domes of the object. Hardness factors characterize the mechanical state of the material, while different zones of the weld joint weight and dynasty different defects and structures. Hardness was developed by the wooders. This is of the resin and the state different angle of 176 degrees in open into the surface of the material that one. This experiment was applied along all the 100 grams was calculated that the material from the applied load to the surface area of the obtained indentation of the rocks were beyond as breathing. Material and microstructural features of the valve. Now, well, the specimen for 09 GUS still motion with this. 09 GUS is a low gravity structural steel represented by increased strength, good loadability and resistance to along the pressure. This item is widely used in the construction, mechanical goods body, and the immersion sector that will manufacture around structures, pipes, ships, and valve joints concise of the different zones. It's never achieved and this knowledge was characterized by the cost of hydrogen structure with very microstructure of the relation could with different degrees of discussion and heterogeneity in the distribution of structural components. Now about results and conclusion. Different results of one joint were studied separately. The experiment involved 6 round specimens of zero language per student. Thus, under the same routing connection. Based on the calculation of was obvious very practical was absolutely that one neither 83.3% of such the average value of practical mention was very the mean value was controlled once quickly. The test results show the average value of practical mention in different zones of knowledge and this may within the range of 1.84.
Нічого не знаю.
Я не знаю. Віталій знає. Віталій знає.
Чекаємо. Чого у вас тут?
Which indicate increased structural continuity and complex frame boundary geometry. Lower values must be of their base level and develop. The correlation between fractal dimension and detail concept properties was established. Those with higher boundaries indicate higher values of the fractal the higher value of the higher value of the fractal dimension reflects the developed trade boundary structure. There are two correlations between the average values of the fractal dimension for the proton and harness compute the existence of a relationship between structural characteristics and mechanical properties. Thus, it was established that long joints All these results will be recognized by the since there is structure the group century together. Very well known and hidden before. The correlation was obtained between the fragment and the structure of components finally very boundaries and individuals of is was use the fractal components as a marker of the events that is separating those owing to their visual and cognitive target. Fractal analysis can be used for quantitative assessment of structural or radiation, mechanical properties, and value process of condition of the condition of the body difference.
Thank you for using so back to the slide where they show the values. Yeah, this one. So perhaps I lost this along the way, but why is this a dependence? 1, 2, 3, 4, 5, these are numbers. It resembles something like the sign problem function, but why? Why? What changes in those 5 samples in this particular magnet?
Well, this chart shows for example,
How do you see that? Just what is the green line? Is it hardness or the structure? Dimensional, fractal dimensional.
This is obvious, where it's in the part of the
For some samples, we have all the correlations. Again, and the indicator is more or less same.
You were talking about measuring fractal dimension using 2D observation of microstructure for well. Is it correct? So you observe the network of grain boundaries. So we work with 2D but the notation is 3D process. There is another coordinate. So how to switch from 2D network and fractal dimension of this 2D network to 3D. In fact, work with measuring of hardness. In this case, it's with 3D. Yeah. No explanation. Okay. Let's see if it's incredible.
that is the one
як працює вимірний і тривимірний фрактал.
Питання розмірність показує на перспективному
Це вам наше. Я заходжу. Може бути.
Можливість
Okay. Magic question question. Question. City. No questions in the once more. Trials, absolutely fine. Dimensionality. That's complex. Option. So we continue our session. The next talk will be delivered on behalf of big number of co-authors, Andrei Mitov. Okay, nice to meet you. Periodic surface structures induced by femtosecond laser radiation. One polished molybdenum single crystal cell. Please, you have 20 minutes to talk. Thank you, Mr. Chairman, for the introduction. Dear colleagues, it's my honor and my pleasure to give to report on the such an expert community of material sciences. I represent Institute of Physics and more exactly laser femtosecond complex, which is the center of collective use of equipment, observational material sciences, laser femtosecond complex in our meeting. At the beginning of the report, I will introduce the possibilities of our center and then we'll show the results, results about the refractory metal structures. So our center was established almost more than 20 years ago. And since that time it works and operates, with many nice results. It's mainly proposed for studies in optics, that is mostly kinetics of fast processes, electronic processes, and also for microprocessing of the visuals. Basic possibilities, laser facilities are complex with everything starts from pumping from that gear, then the card in our complex is layer on fire, then check the pulse amplifier agent, and we have options for ion generation, and as well as second order only generated. So, of course, we have the focus facilities, the chronometers with for the detectors, for different ranges, spectral ranges, and so on, and stability of moving varying temperatures. But mostly our complex can be used for. I would like to point on two parameters of our radiation, protected radiation that I got. This length of laser pulse is about 150 times per second. That means that we can make time result measurements with high accuracy, such a high accuracy. The other key parameter is the power. Our each laser pulse has the power of about 10 gigawatts. You can recognize this power as the total power of all power stations in Ukraine. It's concentrated in so short laser pulse. So this energy, this power, exactly is enough to processing any materials. For time result measurements, we have a lot of developed techniques. That is control, gauge, optical microscopy, laser pulse compression, and so on. It's not a topic of my today's report, just example of many produced homemade apparatuses. But now I will focus on processing of materials, laser processing. This is just few examples of our recent works, that is cutting, of optical materials like quartz, sapphire, precise cutting, some smart surface treatment of silicon, and that will be the point of my today's report, the surface treatment of metals. This is silver, and you can see bright colors on regular polished silver surface. What are these bright colors? Bright colors means diffraction. There is diffraction grating on the surface. This is so-called laser-induced periodic surface structures. Software I will call it FLIPS, and that is the common abbreviation for this phenomenon. The concept is very simple. A single laser beam directed on a surface of the solid produces periodicity. Such a periodicity, periodic structures can be produced on any surface, whether either the metals or conductors or in electrics. The mechanism of wave formation is simple and works, but more complicated today. I have just how it can imagine that process, and that is the picture that the ChatGPT produced in 1 minute. There are a lot of mistakes there, don't take it very seriously, but it can be used to explain main points to this course. When laser beam hits the surface of one horizontal wave is excited. Interference between these two waves, incident wave and surface of one horizontal wave, gives the max interference maximum where something may happen. As we talk about fast ultra-short laser pulses, that is about 100 per second, the energy is absorbed by electrons. Electrons become very hot, and they can evaporate, escape from the source. As the result of less electrons in the source, along explosion can happen. And this is how the ablation occurs. This is so-called cold ablation. There is not a thermal truth. That this thermal effect are minimal in this process. And as a result, we can obtain, as the interference picture, the residual, we have the fleets. These induced periodic surface current. Some basics about fleets. The direction depends on polarization of laser pulse. It's perpendicular to the electric field of the pulse. For central polarization, the structures are maybe set anterior. The period of these structures determined by the defined by laser wave, not mostly. So, for different payments, that you can see 800 nanometers, 400 second, and certainly power laser, you can produce periodic structures which correspond to the longer years. At the same time, the period is little dependent on the energy of the sun. So my interpretation of electrons and the treatment is about little dependence. It's there in the profiles. It's registered and it's back to the table and with the direct to measure the understand. This is part of the period. 250. As for how to produce these structures, focus and value. Typically, such a structures are produced to a historical level, but if we use electrical level, we can increase the area of 1,000.
Напишіть мені,
That is, each our process.
Я сам подумав.
Now I come to REFRACTORY control.
Вам куди я надіслав?
This
читаю.
sample it will be produced in Electric Institute.
Ну,
Follow. And so all questions about how make the crystals and the rest of the references.
щоб вам давати через
But what we have is sample of
камеру.
monocrystalline over them with different crystal plates and different quality of ocean. This is sample like this. Let's say we have plates, size. These are two samples, one on the top row and sample two on the low, on the bottom. And we find such a condenser mode alternator, which depends mostly by the speed of the moving the sample under the laser beam. So it this speed determines the number of pulses, the laser pulses that will keep the focus. So different structures can be produced depending on the number of pulses. For pulse movements, we can produce like a power. If the movement is over, the same power of the laser beam will obtain the dark power. And if we increase the temperature and we take speed, that we can produce such a gradient out of these structures. It was the subject of the study to compare samples of different ocean quality, how they produce things with the dimensions in ocean. To characterize combination with the darkness of the focus, we use instrument non-contact interference profiler produced by the TNT in focus on the National Laboratory of Field Radiation Institute. That use optics for measuring the darkness, and we can refine the numbers of darkness for directional conventional polishing to about 17 millimeters, and for advanced polishing the standard deviation of the surface, or looking square deviation of the surface. And we can see from this reduction pictures the required polishing reduces the light and heat from the light and production efficiency. We also take the samples on the tank. The obviously the difference between the mode 1 when we have other picture and the mode 2 when we have dark, black surface. There is no periodicity and there is periodicity. In the other pictures from this by Fourier analysis we can determine the area of the picture about 500 meters for both different domains. Also we have the structures, how they can be produced from the samples of different crystal traces. We also get the literal sample of the stone, it was about the for all the samples. It's important to say that they all have from the same source. What the question about the impurity of all the about the range. And actually, the fact that difference is little, but still there is. For this area, and the brightest picture, or the portrait was very good to introduce that is for the second. It's interesting to compare here this efficient action efficiencies with the compaction of the real. Interesting that different crystal cases have different quantum energies and requires brightness corresponds to the highest performance. It somehow correlates physically with the idea that we have long explosions in the head of this producing factor. So the escape and reflection from the sources depends on different functions. So it determines the efficiency of this transformation. And so the conclusions that software pollution significantly affects on the quality of the produced leaks, which reduce periodic structures, while the crystallographic index of the software has a little effect in the but still unconfused level. And also our acknowledgement of our politics, national heritage foundational campaign. Well, thank you for your attention.
Thank you, Valerie. Please questions? Please don't certainly know if you are thinking about the questions. I will ask you. So I got in habit to use this second laser just to excite single molecules, just to study the single vibrations in molecules and so on. Never thought about the certain treatments like this. So what was the target roughness you showed? So is it enough? 60 nanometers rough?
That sample looks like almost zero.
It looks visually.
No,
But you are trying to make a very sensitive device.
Okay, sensitive. It's sensitive, but it's fast. It's for that. It's very fast. To produce such a melodic structures like other means, it's difficult for such a part and structure in material. But by doing that, it's even interesting that it's much easier to produce such a practice in factory level than for top level like this.
Anyway, what was the target roughness?
The roughness
And its periodicity?
Good question, because you found this way, even the distance, the better knowledge of what's over, means the better structures will be. But on the other hand, if the software will be ideal with that, there will be software control variables. They cannot decide the ideal to come up with that. Probably we kind of reached the point that polishing, where they will feel that it is good. So there is optimal practice for production of such a structure. But at the moment, I cannot say where it is.
Seems to me the routes much cheaper technologies which provide, the same level of accuracy. For instance, electrochemical polishing. So,
Our point to make polish temple, they would like to make such a erodible structure. Yeah, sure. Polishing is the preliminary effect of providing.
okay. Well, we don't know is very sensitive with respect to the atmosphere. So, but we don't excite or even surface up to high temperatures. In this case, oxidation is not possible or
Okay, also very good question. Of course, the thermal process also can take place in our pyramids. If we increase the power of laser too much, then we can that is start more samples. Also, that is oxidation of the
the variables contributory of oxidation.
all project.
Okay, other questions? Interesting to me. Go ahead. Yeah, go on.
So I wrote a question. So could your leaves realistically improve thermal emissivity or radiation resistance for refractory materials for refractory metals used in near sun spacecraft environments?
Using clips for engaging radiation
And thermal emissivity.
and material. Did you consider, I'm not ready to answer. Okay, that's a good idea, but so our activity. Probably yes, and we have our focus and the activity from our focus will be easier than from this way. But it's difficult to consider. Thank you for the idea.
Other questions? No? Thank you, one more.
Thank you.
It was interesting. So.
Зараз пилипом ще.
Моя тут.
Ні, Антон спочатку. Антона потрібно.
He also representative of patient team of researchers from the Bashkirov Institute of Scientific Physics, National Academy of Science. Okay. You doctor? Okay. So you will deliver us part of the okay. So the electrical properties of nanocomposite ferrum oxides are various chemically and they cellulose suggest.
My name is Louis Bonton. First of all, I would like to for the institute to share our today, I will present our research and the development progress to this point.
Ну, зараз як знайду з телефону. Згадаю тебе з телефону знайду і прокоментую. Добре, давай.
Electric competitors are fluency or electromagnetic waves, but for people they combine the electric and the electric pole. Okay? And we contain a complete our partially program. Due to somehow there is not water of the progress. Therefore, understanding the electric data is important to define for the material. Low voltage electric materials are important for vectors, matters, and systems. However, for electromagnetic performance, the electric losses are difficult because they provide stronger duration of electromagnetic waves. The influence of the ferro, conversion, and thermal annealing remains insufficiently studied. So let's briefly review this publication. The non-composite means your publication means and identify but you have a combined public and there are important and the current is become a variation was to get meets this different composition. The position was performed in carbon and oxygen atmosphere. During water, atmosphere of the water will oxidize about the movement towards the substrate. After the position of the aluminum will form from the new surface, create the structure which follows to mechanisms. And get necessary electric properties to use this control composition. Several types of misuse different terms from circulation brought to the created. In addition to one composite samples, the reference to oxide and oxide needs to go also prepared. The necessary related properties were measured in the frequency range from 5 kHz to 5 MHz using threshold 42, 49, 800. You can see how three samples and 8 reference. The relative close mechanism. The relative close mechanism characterizes the distribution of electromagnetic energy inside the ferro and its conversion to heat. It is determined by relation between imaginary and real particle, the electric conductivity. The relative close constant. The close constant determines the part of incident electromagnetic energy on a material that is absorbed. And the relative of this is original part. The part that the portion of energy dissipated as a heat is within the material.
This slide represents the dependence of the electric loss values on the applied voltage. So, we can observe that the electric loss values increases voltage, especially at low frequency. This behavior is related to increased electrical conductivity and charge carrying spectrum. For fields with high avalanche content, the voltage dependence becomes a point which indicates the contribution of additional polarization mechanism. This involves the material that the field's composition closely affect the geometric behavior. But consider variance of the electric loss function towards the electrical current is increasing frequency. This behavior corresponds to a session polarization by typical for the lower non-control structures. At low frequency, the charge area that enough handful of minerals that are boundary, reducing how the electric place. At high frequency polarization cannot respond quickly in light, which leads to the reduction of the electric loss. The highest the electric loss, well, the initial piece is further sample. Let's review the effect of thermal analysis. Initial piece your analysis at 1,000 degrees Celsius after thermal analysis. The electric loss increasing significantly for not sample. The problem increase was conducted at least started to information 1-to-1 and 1-to-2. This effect is measured in separation and following additional interfaces. The further analysis of start. This interfaces becomes Maxwell polarization and increased charge areas, which result in strong electric loss. In conclusion, the electric loss is silicon oxide and carbon oxide non-convergent fields can be depend on frequency, voltage, composition, and thermal energy. The electric losses increase with increasing voltage and decrease with increasing frequency. The current to free conversion significantly increases the electric response of material. After thermal energy, you can see the significant increases of the electric loss from local samples. Thank you very much for your attention, and I will take it on to your attention.
Thank you very much for the talk, Anton. Questions to author, please? Bioelectrics is a complicated field of research. I know. My question was, what will be the great size of the field of iron oxide? Your film has grain size position. What was the grain size in oxide?
Oh, about 140
nanometers.
Yeah.
This is not the single domain grains, right? Or iron and such. Before your comments should include this feature of grains and domain structure. You didn't comment the dielectric losses because of these grains, grain boundaries and so on. and multi-domain structural things. What do you think about? Oh, you have quite a high level of dielectric forces, time delta.
Yeah. The removal that I need to do
No, I need to comment about behavior of dielectric forces. And I think this parameter connected with grain structure of stones.
Yeah. Composition of and silicon.
Yeah, because there is the polarization field in this case, if you have boundaries and domains inside. Another question. Thank you for the talk.
Thank you very much.
Yep. And the last talk, before the break, will deliver Valentina Nosenko. She is representative of Flash-Karel Institute of Semiconductor Physics, National Academy of Science. She will deliver a talk about systematic investigation of paramagnetic centers in copper velvet zirconia nanotron. Yeah, you're welcome.
Thank you so much. Thank you for the opportunity to be here. The topic of my report is systematic investigation of paramagnetic centers in copper nanopowders. I present the results of the group of researchers from the Flash-Karel Institute of Semiconductor Physics Technical Center and Frantsevich Institute for Problems of Material Science. Sorry, I just tried to figure out. Okay, so why do we study zirconium dioxide? It is well known that due to its unique properties, the zirconium dioxide is widely used in protective coatings, sensing, and catalysis. Recent years, a considerable attention is paid to obtain doped zirconium oxide. The main idea is to obtain the materials with target properties. For example, doping with rare earth elements enhance luminescence and thus enable zirconium dioxide used in light-emitting devices. Incorporation of copper significantly improves catalytic efficiency. The key question is whether copper is incorporated into the zirconium lattice or form surface components. That's why the goal was to conduct systematical study of the nature of copper-related paramagnetic centers in zirconium dioxide powders and to analyze the influence of technological parameters such as calculation temperature, dopant concentration, additional heat conductor on the center's formation. Materials were obtained using the copper precipitation technique. We have samples with copper content and also have samples which were doped with copper and yttrium. For characterization, we use EPR, NMR, and Raman techniques. Here are the details. Next slide demonstrates the EPR study of zirconium dioxide doped with different copper content. Upper experiment, lower heating. You can see that experimental spectrum has different light shades. The detailed analysis shows that the samples which were doped with low copper content up to 1% can be described as using just one single component. Sorry, with the signal A default. So if you see that this line have a figure slice written into 4 lines, which is characteristic for common to plus ions. This heterophile split is caused by heterophile target of unpaired electron with the copper nuclei. Here are the parameters. These parameters are rather close to the parameters of these two complexes. I will answer this question a little bit later. For the samples which were both with high copper content, the spectrum cannot be defined just one component, use one component. For good fit, we need to add another signal, we call it signal D. This signal intensity increased with the rise of copper content. That's why we can conclude that this signal is related to the area with copper enriched area. In this area, 4 ions situated close to each other and coupled by the volume of exchange interaction. To find out the exact nature of this signal, we carried out measurements at liquid nitrogen temperature. It is known that intensity of paramagnetic signal depends on the measurement temperature with Curie law, previous law, while the intensity of superparamagnetic signal depends on the weakly depends on the measurement temperature. This measurement allows us to conclude that the signal A has the paramagnetic nature, while the signal B demonstrates superparamagnetic behavior. So it is associated with the copper-rich elements of nanoclusters, such as metallic copper or copper located on the surface on zirconium dioxide found as granules. Next slide demonstrates the inert study of copper and copper ion doped zirconium dioxide nanopowders that calculate at different temperatures. You see that calcination temperature drastically influences on light shape of the spectrum. For the just copper doped samples, the intensity of signal A decreased with the increase of calcination temperature and almost disappeared at 800 degrees. At the 1000 degree, the set of narrow shaped irregular form lines observed. This signal C, I will show you, zoom into this signal, is related to the copper to plus ion in the monoclinic zirconium oxide lattice. So, at the high concentration calcination temperature, the destruction of copper-related surface complexes promotes the incorporation of copper to plus ions into the bulk of zirconium dioxide nanoclusters and the zirconium position. And now about the issue. Issue is usually used to stabilize the more symmetric zirconium dioxide phases, such as tetragonal and cubic phase. That's why it's very important to understand how the incorporation of each will influence on the paramagnetic copper-related samples. We show that in co-doped samples, copper to plus incorporates lattice at the lower temperature as compared to the samples calculated just with copper. In the signal with the same copper content, the maximum copper incorporation is observed for the samples doped with 3% of yttrium. Explanation is that yttrium leads to formation of oxygen vacancies requires for dopant charge compensation, which facilitates copper diffusion. At high yttrium dopant, 10%, we observed depreciation effects. So lithium compared with copper for lanthanide, making copper incorporation more difficult. That's why this blue symbol is less intense. Next slide demonstrates the nuclear magnetic resonance study of our sample. We carried out the study to answer the question: is the signal EA is related to the complexes of copper with water or with large loop? This what was observed that for all samples calculated at 400 degrees, and our spectrum is caused by two bands. First, blue one is related to two protons of water molecules on the oxide surface, and the second red one corresponds to zirconium large loops. At high concentration temperature, 600, water signal drops. So the escape of water molecules is accompanied by the sharp decrease of the EPR signal A. That allows us to make the conclusion that signal A is related to the forceful surface from water complexes. Next slide demonstrates the random study of our samples. We carried out the study to perform our model of the signal C, namely that the copper to plus ions incorporate into monoclinic lattice of zirconium dioxide. To analyze the spectrum, you just need to know that this doublet is the field prints of monoclinic phase, and this band corresponds to terminal phase. So, at 1000 degree, Raman demonstrates the domination of monoclinic phase, which correlates with the increase on signal C in EPR study. At 600 degrees, Raman shows the contribution of terminal phase and absence of signal C in EPR spectrum. So it confirms our model of signal C. And now the conclusion. At low calcination temperature and low copper doping, the EPR spectra are caused by the surface from water complexes. If at the same calcination temperature, but at higher copper loaded up to 81%, the additional superferromagnetic signal caused by the copper clash is observed. At high concentration temperature, surface complexes are destroyed and the copper to plus the ions incorporated into the monoclinic zirconium dioxide lattice. Covalent with yttrium facilitates copper incorporation at lower temperature by creating oxygen vacancies. And I want to stress that doping level and calcination temperature are effective too to tune the surface states for better catalytic performance. Thank you very much for your attention, and I also would like to thank National Research Foundation for support.
Thank you very much for being on. So nice to hear you talk from how it was on research.
It had quite with our levels, it also had one and also this depreciation and housing is localized, which should have another dependence of the microgrid level, and probably there is also an answer.
Yes, we all did it. We also can, like you said, different power dependent to show it. Sure.
But it clearly does. If I read the question about the dot, the dot form, you say that there's an copper is introduced into the lattice in monoclinic. Is it an incorporation or substitution?
It's substitute zirconium, since the position of the zirconium,
Okay,
but in monoclinic phase
it's in a monoclinic phase in zirconium supply.
position, yes.
But you also say that doping with 3% yttrium reduces the temperature of incorporation from 1000 degrees centigrade to 800 degrees centigrade. So yttrium in this concentration, I'm not sure how much it influences this stabilization, but probably tetragonal phase is certainly at 800 degrees already done. Of course, you need up to 8% for cubic phase stabilization, but 3% probably to reduce the amount of monoclinic phase in the sun. So why the temperature drops?
Just know that each one, when you put it beside it, creates oxygen vacancies. So by these vacancies, the incorporation of copper becomes easier. But when the amount of the yttrium is higher, then they start to convert one to each other.
But this is a little bit perhaps counterintuitive. The copper starts to diffuse through the oxygen sublattice. Yes.
Not sure, it's just it helps to diffuse.
So more space or like that?
Do you have evidences that lattice parameter changes?
No, I don't have it's just measure at the back of the samples.
Okay, thank you.
Any questions? Interesting topic, in fact, because zirconia adopted with various transition metals, oxides, of course, are considered prospective polygatalis, polyoelectric catalysts, and you are talking about joining some OH groups or sometimes vice versa, OH radicals to be productive. So in this case, no changes in oxidation degree of copper because this plays like the electron pump, sometimes very fruitful for electrophotocatalysis, for instance.
We just show that this signal in the art, so it's related to copper water complexes. So we just show it, and we also know that for catalysis, it's the surface complexes plays the main role. So now using our samples, we just need to go and check which temperature will be. So we know that these complexes are with water, and to check whether they play the main role.
What was the particle size?
It was 15 nanometers now.
Oh, okay. So it's always charged negatively. And if you have OH groups on the surface, if you go down with size, it should be recharged and become lost. Positively charged surface.
We don't have OH group, we have with water.
It doesn't matter. You don't have water anymore on the surface of nanoparticles.
Or
What is easily splitting, huh?
you don't have water anymore on the surface.
Yeah, indeed, what is splitting will be a non-particle surface. So probably you will find other effects in your objects. Sometimes in transition metal oxides, including into the lattice, zirconia or similar oxides, recharge the surface. So if you adopt zirconia that's negatively charged, and with the same particles, additives of transition metal oxides recharge to the positive charge. So, other comments? Other desire to have a question? They want to give up? There seems to be okay, good luck. So we end the morning session and waiting for Professor Devosi with his presentation after lunch, sorry. Yes, after lunchtime. So I announced the break for lunch. Yeah, and the next The next presentation, we expected 15:20. And the afternoon session will be fully
Okay.
I know it's the same. Okay. We are waiting for Professor Gilles. Thank you very much for listening. Thank you.
До 15-20 видоскопів.
У нас постерно зараз же ж. З другої до третьої. Да? У нас же ж постер з другої до третьої.
Ні, після обіду у нас
Зразу гогоці буде?
а потім просто. А ні, чи ні?
Ні, у нас по цьому.
Ви определитесь.
По цьому у нас він.
Постер?
Да. Якщо по онлайну. Ось десь ланч, постери,
А,
з
ну,
другої
да,
до
третьої.
а
так.
потім кова брейника.
Гогоці.
Це я просто слухаю, я так не розумію.
Так я тоже думаю, да,
Я
собираемся.
думаю, може останні зміни. Які там,
Я ж тоже
в
думаю.
останній момент змінилися. Ну, постери буду постери.
Не, ну как-то я слушаю, думаю, 15-20 собираемся. Думаю, как-то вот то ж вроде было.
Раз, два, три. Один, два, три. Раз, два. Раз, два, три. Раз, два, три. Раз. Раз, два, три. Ветер, закривайте там, не добніше було. Закривайте, що вона буде вам заважати?
Position based in silicon and 4 T and chemical and electrophysical thermal nitidation of components of TCU for their synthesis in vacuum at temperatures of conditional silicon operation. And it should form a homogeneous construction of titanium nitride and silicon crystal. Demonstrating a reaction of TC2 occurs according to the equation complete incorporation of the theoretical amount of it again is ensured by closing all 11 into positions. This corresponds to 33,000 nitrogen or 100,000 degree of integration of the products. The results obtained are given in the table. Experiments. Conclusions. The temperatures of 1,000 17. The data is dated to two position, starting from 170.
1470.
For more positions, you can upload it in each weekend. By arbitration of analysis and the direct certification of the injection production.
Thank you. Are there any questions to present? Thank you very much. One moment. Is it prospective sensor for nitrogen for future?
So,
What do you consider this direction? The silver side of titanium and nitrogen. Is it high temperature sensor?
high temperature for CPN. That's titanium and
Yeah, you promise us this one. Sensor, we should have got it. It's the reason for gas chromatography. This is automated. Just this is suggestion that it could be gas and nitrogen sensor for it. It's more the method of determination of the amount of yeah, it could be used vice versa for the same purposes. Just characterization with gas chromatography and simultaneously it could be used like a sensor. But to my mind, that it's much more sensitive with respect to oxygen. I think we would probably move this faster. Okay. Next one. It's yours.
Now the focus resides on the concentrated service with this we get such properties of such composites. You can see that as the parts of another side, concentration of oxygen in this system. When we investigated properties and the feature has the most the better. This photos is interested the composite founders, but on the surface of this composite photos we have only boron oxide acid, boron acid. So on the surface. But on the other side, when we made the X-ray diffraction study, we discovered that this composite materials consist from boron nitride, boron oxide, boron acid, and the oxides of this elements, which was added to the initial boron. Moreover, this powders has such morphology before heating. You can see that this powder with chromium display the elongated structure. So maybe because of that we have the best kinetic properties of this composite materials. And we investigated after we made heat treatment before investigation of this electrochemical properties, because it is necessary to save this powders on the surface inoxide, because it's necessary to add this coating to make it inoxide.
Stunning.
It's inoxide, yes?
Yes.
Because I don't remember. That is why after heating we have the same properties, only in the case of alumina, we did not have any oxygen, any other oxide, any alumina oxide. It's tells us about that during this experiments, alumina interact with acid. So as a result, we don't have alumina on the surface. And so we have very such properties. This properties is better than tinoxide. We have tinoxide. What? So another
Relative.
Yes, relative properties against tinoxide. And this is the best results. It's demonstrates of us that materials with chromium is the best, because we compare these materials with pure chromium oxide, and we can see this pure chromium oxide during cycling disappearing. This two chemical properties disappear, but materials with chromium oxide and this one continue to run. So it tells us about how to say stabilization of catalytic properties of any of the elements. Oxide.
Or vice versa, poisoning. Okay, tell do you have a comparison of specific surface area for all? Are they equal or big difference between them?
Should make this research, because it's not possible. Quantity not so big, so we cannot compare surface. But look like this materials with chromium oxide is more surface.
Will develop specific surface area. Have you measured the pore size distribution? I guess it's option. No?
Not possible, not
Because I understand. So
just result.
it must be very helpful, this characteristic, because such objects they're usually mesoporous or microporous. So, and they catalytic activity is strongly advanced in this field.
Yes, but I like in these stages editing of the form used to stabilize properties. So it's not only surface, it's just form maker, because the body creates special structure. And this structure save properties of the catalytic elements.
Okay, other questions? No? Thank you
Thank you very much.
What's the next?
Is this one yours? No, listen. Or the work. So, good evening. We want to present our topics of effect of heat treatment mode on phase transformation progress in nanoscales scales palladium with silver ferrum. Our motivation is to create ultra high density recording media material, and for this for heat and sided magnetic recording means and spectronic application. We use an additional layer of element as intermediate layer between ferrum and palladium. It's significantly affects on the creating of ordering phase. And our aim of this whole study was to research how this influence the heat treatment mode and annihilating temperature on our structure. So for experiment, we took nanoscale fields of palladium, argentum, and ferrum. Argentum is a layer between these two to change to ordering our phase to see how it changes. We annihilate. We use a heat treatment by 3 methods. Rapid thermal annihilating in nitrogen for 18 seconds and annihilating in hydrogen in range of temperature of 600 to 700 degrees for 1 hour, and both stages by RTA and annihilating hydrogen. After that, we used X-ray analysis with and AFM methods. After that, we got our results where we can see how changes our phase from flat from flat on the one phase of palladium. We got 2 phase structure, ferromagnetic. Sorry. Forgot this word. Sorry. So we got not structured A1 phase in as deposited compression or a break peak of low intensity from palladium is visible on the X-ray pattern. After RTA, soft magnetic phase forms in films in composition with RTA during the heat treatment in a hydrogen environment, temperature 600 degrees. A disordered A1 phase and ferrum palladium heat rate are formed in the layer. We can see how this formed this disordered phase. Average rows of film after annealing in hydrogen 650 degrees is near 40 nanometers scales, and we can see change like this. Two-stage heat treatment at temperature 600 degrees and 650 degrees also lead to formation of the A1 phase and does not change its magnetic stage of the layer of ferrum argentum composition. It was established that during hydrogen annealing, the temperature increase to 650 degrees and 700 degrees leads to decrease in the saturation magnetic in the palladium films by almost 2 times. At the same time, the film remains soft magnetic stage all the time.
What was the grain size right after the depositing?
The grain size?
What was the grain size right after the depositing of your show ASM?
We have almost flat side, flat structure surface, yeah, and this surface with annihilating and increasing the temperature was more not flat road. As we can see by this graphic, we can see how it's changed and getting bigger.
Is this oxidation annealing in what atmosphere? In hydrogen?
Yeah, we was annealing in hydrogen, and it's not about oxidizing. It's more about changing our surface. It was
This is average, right?
yes, right.
So
It was increasing with increasing temperature.
this is on surface graphics.
Yeah.
How about Professor Verbulis question on the grain size?
Grain size. Oh, yeah. With grain size, we have this small graphic which shows we got grain size of bigger than 650 degrees and got again smaller up to 700 degrees.
What is nanometers? So this is defined from the sardine measurements. Visually, it's
We use X-ray diffraction, and after that we got
even on the XRP.
yeah, yes.
Any other question? Thank you very much. Two bigos. Grains of the big.
Let me introduce our work on the influence of physical-chemical processing for the change of properties of synthetic diamonds. Our work was to obtain high-quality grinding diamond powders with high content of the main fraction of individual grain and with high uniformity in their linear dimensions. It's important to improve their physical, mechanical, and chemical characteristics. Diamond powder of individual grain size are subjected to selective crushing of eliminated doubles and weak defective grain and when in the planetary medium. Our research was conducted on diamond grinding powder on the RS80 grade with grain size 1 grain size and AS32 grade with another grain size and AS6 grade. We measured with different methods like specific magnetic susceptibility, with using the Faraday method and hydrophilicity and other. You can see on the poster. So we first of all we research our methods for understand what we have physical chemical characteristics our diamond in initial, and then we use narrow grain size, and then we research surface characteristics of our diamond grinding grains, and we found that this grain have pores, and it's we can see it's, the graphs. Yeah. In this method absorption isotherms, we can see that all these grains have measurables, and what next? The next step was use it grinding powder in grinding wheels, or use in grinding process with hard alloy BK6 or BK8, and so what we can see, we see the initial grains what we have, then we get with our methods we can see narrow size, and as a result we can see that initial not initial narrow size is better than initial, because that powder has more pores or defectives, and these have more shapes our grains. So and the conclusion.
As you wish.
So conclusions. It was found due to the destruction of weak defecting grains and additional distribution of sieves and separation of grain shape. It was found the obtained narrow grains size grinding powder with a specific surface area less than original powder by 11%, and for another grains by 5.5%. It is shown that the pore size for diamond printing of narrow grain size decreases in comparison with the original initial powder, and approximately 0.2 nanometers, and for narrow size is comparison by 0.75 nanometers. It was found that diamond of AS32 brand with a grain size have lower relative diamond consumption and roughness of the treated surface compared to the original grain, due to the increase of grain belonging to the main fraction and their strength index. As a result, increase wear resistance of grinding glue.
Thank you very much. So, just to clarify, the size, the average size of the grinding powder change.
Not a small average, not average.
Just the distribution.
We have initial grain size with high and low sieves. So it's called 100. It's high sieves. 80 it's low sieves. Yeah.
So the middle,
Yes.
everything that went through the 100 mesh and was left on 800.
Then we have sieves under 100 under high and low. Yeah, another sieves one, and then we got our powder with narrow size, more precise. Yeah. This precise powder has more precise liner dimension. Liners.
It's clear.
Yeah.
There are just not so many variants in the size and shapes.
Yeah. Yeah.
Then you are, as I understood it, you are telling that the surface quality of this more narrow size distribution is different from what the rotors.
Surface.
You said defects, of course, on the
Yeah,
surface.
yeah.
And what
We use defects in our powder grades. Defects, yeah. Like to methods to decrease our work, our instrument.
decrease. Log. Okay.
But why? Because we need some roughness our we have more homogeneity in our powder grains.
Yeah.
So no increase our work. but
That was surprising.
yeah, but decrease for our roughness.
Decrease of the roughness of the surface.
Yeah.
And at the same time, increase in the
More to our
okay. I think we will need to discuss it. Thank you very much. Yep. Now.
I would like to present the presentation, low dimensional electrolytic building and PCB and introduces one about electric analysis of hydrogen reduction via water elements. Aim of our study was studies the characteristics by polarization cathodes in Corliss method from ground to the PCM and grounding of the drives in electrolyte 0.5 sulfuric acid. And determining of the possibilities of using the result is the development of the new laboratory management electrochemical exploration to preparate the nanocrystalline process boundaries. Providing recommendation for new nano heterostructural design with synergetic effects of electrical properties. Mine results for electrochemical disruptors and Micron and dispersive to the novel disseminated orders and Micron 1G neopis triselenite representative of figures. It's more maybe for results. Because who want and anyone can find more on our presentation. I say my results. Yes. For the 2D novel disseminated from powders with metallic conductivity that are characterized by sufficiently high values of electrical conductivity, which indicate the promising potential for the use in nanocomposites, nanoelectrolysis for hydrogen production in water electrolysis in high cooling density. This is an important characteristic of scaling up laboratory techniques. Obtained result indicates the promising potential for the future research on the development of laboratory technology of electrochemical dispersion of novel disseminated Micron powders, quantification of protons and water molecules. Such processes under controlled kinetic conductions also elimination of particle along the length plan. This were way to otherwise opposite act and fragmentation of many formed nanoparticles. We solved to lead to the formation of nanocrystalline of interpolation path of variable composition to H because we have structural type to H fatalis and Y like 0 or 0.29. Yes.
Really
Sorry. And it's for the noble bismuth and for the noble 3 it characterizes it by high current density values and moderate cathode potential values. Promising for the creation of electrocatalysis capability of operation at the high current density, high electrical conductivity, are considered interested for the creation of multifunctional nanomicrocomposite with the mixed dimensions, 1D, 2D. For example, 1D nobis triselenite, 2D nobis biselenite. Growth of lemon, those single crystallines of 1D nobis triselenite are capability of dispersion in the process of electrochemical interaction, co-interaction of protons and water molecules. This can be used in the development of active nanotechnology. And summary, it was shown that 2D nobis biselenite and 1D nobis triselenite are promising objects for the low dimension electrocatalysis design that during hydrogen conduction during water electrocatalysis at high current density. This is necessary for scanning for laboratory technology. And we want can find more on these posters.
Thank you very much. If I may, I would like to question about the combination of these
on 1D? How does it work? Because 1D is a really tiny object like nanodot or something like that, where you, what does it mean? Is it the fiber? What is it? What does 1D means here? Because my phone is this size. Yes.
It's a configuration, 1D and 2D is configuration folder. No, 2D is 1D,
layer.
it's 1D.
2D is layer.
1D
2D is layer. 2D is a surface, so we have one measurement and
Yes.
this is called 2D. So my question is 1D, what does it mean? Because nanotubes are probably 1D.
No, it's powder, but in this case, it's a monocrystals. We have one big one. In other, it's powder, but they like
Filaments, needles.
it's like that. But we do electrochemical.
What are the sizes of those needles?
Sorry,
They are micron in this size, but what are the cross
can't
sections?
say this because I do electrochemical
Parts.
parts and maybe because it's powder we take from other people
And they call it 1D. Okay.
Sorry.
Ask them why is
Yes,
it 1D?
maybe I'm going to talk.
Thank you.
They wanted to apply this anode material. Is it anode material?
Yes, no, it's for hair. We take this for hair.
HDR, yeah, hydrogen
Yes,
reaction. Hydrogen release reaction.
for gain energy or like.
Okay, thank you. Thank you very much. Maybe other question? This one perhaps belongs in the other session, no? Right. No, today? Yes, okay, it's about not. So tell us.
It's to be.
Can you tell us a little bit about?
I want to present our research first principle study of modular boron nitrides. 2D hexagonal boron nitride has a unique combination of properties, thermal stability, foundation from 2D device. This material has wide application in electronics, thermal management, optical electronics, energy applications, protective coating. Research and this work aims to examine the structure evolution of 2D hexagonal boron nitride under tensile mechanical loading and subsequent destructions. Research method first principle modeling was based on the density functional theory approach implemented in the quantum special software package. We modeled uni-axial tensile strain applied along the x-axis and uni-axial tensile strain applied along the y-axis. In that direction, X regular tensile deformation occurs up to 0 0.4 strain, and the strain 0.4 and 0.5, the elastic failure accompanied with the formation broken instruction structure in observer. The calculation tensile force per length strain in x direction for hexagonal boron nitride monolayers and enthalpy with strain in x direction from hexagonal boron nitride monolayers. A sharp change and the strain 0.45 is associated with breaking the structure in the direction y at the strain 0.3 the course structural change to order orthorhombic structure formed 1D boron nitride threads. Calculation tensile force per length strain in y direction for hexagonal boron nitride monolayer. The behavior of force and enthalpy of the hexagonal boron nitride strain in y direction, relevance and structural transformation above the point 0.3, the force assigned a chance indicating the onset on the repulsion in the system. In the density of states of monolayer boron nitride in the direction x, those strained system after structural transformation. In this case, the system represent a set of weakly in interaction 1D boron nitride threads. Conclusions: structural transformation in 2D hexagonal boron nitride monolayer subjected to tensile strain are investigated based on first principle calculation. In X direction, we have elastic fiber accompanied with the formation broken disordered structure in observed in under tensile strain in the y direction. We have result in the breaking of the hexagonal lattice in the formation or 2D orthorhombic structure formed by 1D atomic strings nano threads. The calculation of force and enthalpy indicates the presence of repulsion in the system. Therefore, its structure is unstable. The simulation evidence that the tensile strain result in the decrease of the band gap in hexagonal boron nitride monolayers.
Thank you very much. I have a question, which is not a question, actually, just to discuss. So it breaks at 0.5 or something around that, between 0.4 and 0.5.
Yes.
This is actually impressive. So you can stretch it almost 75%.
Yes, yes. We modulate the ideal structure. We have theoretical calculations, but
that's our common problem. We have I don't doubt that. That is a question which is often asked by experts. But how come
But it doesn't necessarily correlate with experiment. It does, of course. Experiment is difficult, it's purely theoretical. It's difficult to know such situation. And I think if it could be done, they wouldn't manufacture information, special formulation. Okay, thank you very much. Any other questions here? No?
In this work, yes, it's mine. In this work, we investigated stationary value-based solutions and innovative materials for generic and multi-performing applications. We studied compounds the value in various nanostructures, to have the same symmetry. We combined experimental and theoretical methods, including vapor spectroscopy, optical absorption measurements, and deep calculations. Our results show that bands are dominated by coherent states S3P or SLN3P, while Dali shift states all investigated compounds exhibit semiconductor behavior with values in the range of 1.3, 1.4, 1.5 electron volts, making them promising candidates for several applications. In addition, the materials demonstrate strong optical absorptions and good agreement with experimental and theoretical results.
So 1.3, 1.5. Again, is close to what they need in solar cell. You said the material is promising for cellular applications. What does it mean?
Solar cell.
For solar cells. What advantages does it have in comparison with silicon cells? No, I mean, are they going to be cheaper or more stable?
Cheaper. This
solar cells, what are they made of? Typically, regular solar cells. What do they use for solar cells? Chinese solar cells on the roofs.
Break.
Sure.
So yeah. На тому комп'ютері є, все. Почав. А це треба туди йти, щоб розводити.
Good morning, Yuri. Please meet Professor Yuri Kurotsky from Drexel Nanomaterials Institute. He is director of this institute. With the presentation, keynote presentation, building blocks for technology of the future, not sense and beyond. Very, very nice to see you from the United States of America. We're also happy again to meet you in our conference. You're already a well-known person through this conference for many years, and and my pleasure that we meet the laureate of SAMSONOV Prize on the Material Research Society of Ukraine. Today I propose excellent and very attractive topic for presentation. If you have 40 minutes, please, we are waiting for interesting talk.
Андрій, дуже дякую. Я розумію, що це конференція міжнародна, тому мені треба виступати англійською мовою. Я не бачу жодного науковця за кордону у Zoom, але розумію, що може хтось є присутній. First of all, thank you very much for the invitation. It's a real pleasure to participate. I know it was a very difficult weekend in Ukraine, in Kyiv, particularly Saturday night, with all the distractions here. And my help, like sending part of my salary to Ukrainian armed forces every month, speaking, collaborating is very small. But whatever I can do to help, I'm always glad. And particularly, I used to work at Institute of Material Science. I graduated from Kyiv Polytechnic, and I'm glad to connect, at least online. Let me share my screen. Okay, good. You need to allow me to share my screen. Андрій, я не можу це зробити зараз. Ще раз. I see a message, sharing is not turned on. You need to turn it on. Мені треба від вас дозвіл, щоб я міг мог показати свою презентацію.
Скажіть, що зараз зробимо.
Є вже.
Є?
Чітко.
Хтось, мабуть, ще доповідає. Воно каже мені зараз, the host isn't allowing multiple presenter sharing for this meeting. Хтось ще, мабуть, також вимкнув sharing.
Декілька хвилин.
У когось ще на комп'ютері sharing зараз. Він мені каже, the host isn't allowing multiple presenter sharing for this meeting.
Колеги, заставка матеріалознавства товариства розшарена.
Тоді вам треба заставку цю вимикнути.
У мене все включено. То що говорить?
Ладно, що нічого не виходить.
У мене все включено, я не бачу. Чогось.
Заставка – це можливо, що воно не дозволяє мені війти. Чи коли можете, дозвольте, щоб багато президента разом могли шерінг робити?
Давай, все спочатку. Через сеттинг. Було так. Все є. Choose individual. Що за choose individual? Not once. Screen share focus compliment. То скільки оновлення, воно щось по-новому взагалі.
Зараз ви вимкнули, зараз воно мені показує sharing is not turned on.
Написано, типу, будь ласка.
І зараз multiple presenter. Тому це визначає, що хтось інший, Остап, свій комп'ютер вимкнув. Це може, мені показує, це Frantsevich і МРС, може вимкнути цей комп'ютер, коли це інший комп'ютер. Я не знаю, ви свого комп'ютера показуєте.
Професор Голодці, спробуйте зараз.
Окей. Працює. Добре.
Все включено.
Бачите мою презентацію? Окей. Супер. Sorry for this technical difficulty. I think it has been resolved. So basically, I'm planning to do an update about our research on MXenes, family of two-dimensional carbides and nitrides we discovered at Drexel University 15 years ago. And for people who don't know about Drexel, so I moved to Philadelphia in year 2000. So I studied in Ukraine at Kiev Polytechnic. I worked at the Institute of Material Science after graduation. And after going in 1990 to Germany as a Humboldt Fellow, I kept traveling. And for the past 25 years, I've been working here in Pennsylvania, in Philadelphia. And this is the first building of Drexel University. You may find it somewhat similar to Kiev Polytechnic. It comes from close age 1892 and also used to be Drexel Institute, basically Polytechnic University. And our strength is really nanoscience, material science, physical chemistry. In impact of our research, in latest US News and World Report, we were #1 in the world. And we are number 32 in the world in Shanghai ranking, for example, in material science. So our strengths are really materials, and I'm glad to speak at this conference. And Grigory Samsonov is really the founder of the field I'm exploring now, carbides or nitrides of transition metals. And our work is really following footsteps of Samsonov, and I'm truly proud to speak here at Samsonov conference to honor his memory, because I worked on carbide and nitrides and barides and other refractory compounds after graduation from Kyiv Polytechnic in Ukraine. This book is based on my older work, bulk carbides and nitrides. And I continue working on carbides and nitrides, MXenes, now. So we took it to two-dimensional state, from bulk material separated into atomically thin layers. MXenes are a big field now. There are many, many books published on MXenes, edited in different languages, Chinese, Hindu. Have not seen a book in Ukrainian yet. I'm sure one day it will come. We have a new book edited now with my former postdoc and a colleague from the Emirates on hydrogen technology. So it's growing very quickly. More than 30,000 papers, more than 10,000 patent applications, pretty much all over the world. And MXenes are really a part of a very large world of two-dimensional materials. This is a very recent paper we published with a number of authors, combining experimental and computational data for 2D materials, because there are so many of them. Dichalcogenides, oxides, of course, elementary materials of different compositions, more complex structures. And of course, MXenes are here. I look at all those materials and building blocks for the future materials devices, because by taking 2D materials and putting them together as bricks in the wall or Lego stones, we can create combinations of properties that no single material can do. Moreover, we can now computationally predict properties of many of them and properties if we combine those materials. So really, we're doing computational design of new materials of a variety of compositions using MXenes, but also other materials. What is interesting, even in this like 6-7 years ago published article, MXenes were already on the cover Chemical Engineering News. It's a magazine of American Chemical Society that goes to like 170,000 people around the world as a cover materials. There was a special issue dedicated to MXene 2 years ago. So they are playing an increasing role. And one of the reasons is that there are so many of them. It's a very, very diverse family. We can have from 2 to 5 atoms of transition metal. Those are the metals possible on M position. So M stands for transition metal. Lanthanide recently were also demonstrated. X element connecting M atoms, small dark dots, carbon, nitrogen. Oxygen can substitute for them. And on the surface, we can have halogens, chalcogens, hydroxyl groups, oxygen, pnictogens. Arsenic has been predicted, not experimentally yet shown. Actinides, some of them have been predicted, not shown yet. So basically, we discovered 15 years ago titanium carbide MXene. This was the first paper. There are about 50 compositions, simple one, MX known, over 50 solid solutions. But if you just calculate number of possible combinations, forget about thermodynamics for a moment. 4 structures, a dozen of metals, let's even ignore lanthanides, carbon, nitrogen, it's 96 combinations. Multiply by surface terminations over 1,000. And thermodynamic calculations, this is a result from our work with collaborator from my university, Professor Yonji Hu, show that again, we can get about 1,000 of either stable blue or metastable compositions carbide nitrides, just simple ones. But we can make solid solution on M side, solid solution on X side, carbon nitride, oxycarbides, oxynitrides. So really sky is the limit. We can have variety of metals, we can have variety of terminations. Actually, without terminations, MXenes are much less stable. Those are really surface terminations that stabilize them. And that's very, very important part of what controls the properties. Now, just to show what is possible, we published this article in Science last fall in September, showing we can get up to 9 different metals in high entropy MXene. It's probably the most complex 2-dimensional material ever published. So we can create infinite number of materials, but we really need guidance from artificial intelligence, from machine learning, other computational methods that predict what the properties are. We cannot experimentally make an infinite number of materials with all possible elements. So we are entering the era of computer-guided design and potentially also robotic labs, which will make all these new materials, the building blocks for our future. Moreover, many of them can be made with abundant element. Titanium, for example, carbon, nitrogen, oxygen on the surface of sulfur, chlorine, fluorine. These are very common. So what it means that if we have a scalable method, we can produce them at relatively low cost. So what I'm going to do in the rest of my presentation, I will talk a bit about synthesis, properties, and give some examples of applications. First, how we make MXenes. In our very first paper, we used hydrofluoric acid, HF, to etch so-known MAX phase, layered titanium aluminum carbide. I know many people in Kyiv at the Institute of Material Science, Institute of Super Hard Materials, are very familiar with MAX phases, work on them. I saw Tatiana Prikhna join the presentation. But this etching leads to hydrophilic flakes of MXene. But we can also use halogens, gases, molten salts, or we can use chemical vapor deposition to produce MXenes with uniform halogen surface termination. These are hydrophilic. This will be hydrophobic. So method of synthesis, surface chemistry, control the properties. What is important? We can make them in sufficiently large quantities even in the lab. This is my former postdoc, professor in Texas now, John, holding 1 kilogram of titanium carbide MXene. And this is my current student holds probably like about 6-7 liters of solution, of colloidal solution, of two-dimensional MXene flakes. We started a couple of companies in the West of my former student, we started MXene Inc. Canadian colleagues started MXene Dynamics Corporation to use MXene that we produce. In Ukraine, Center Materialoznavstva, MRC, Carbon Ukraine have been providing under license from Drexel University MXenes to many researchers. They sell it to hundreds of organizations around the world. So production is available in Ukraine, at least for research purposes at the moment. Now, what is also important? Traditionally, we required max phases to make max. However, nowadays, we also make it by gas phase reactions, by mixing titanium chloride with natural gas, and we can make again titanium 2C, several other carbides, but also nitride MXene if ammonia or nitrogen is used instead of gas. Why this is important? Titanium chloride is intermediate product in synthesis of titanium. Millions of tons are produced every year. Natural gas is available and very cheap. So what it means that if titanium oxide, if carbon nanotubes are produced by the same method, pretty much, we can make MXene in very large quantities and at very low cost to make it a commodity material. Now, we can make almost infinite number of compositions, many of them from abundant precursors, in highly scalable methods, which can also become inexpensive at very large volume production. So what is unique about it? Why we care? What properties they can bring to the table? One important thing, MXene flakes are very strong. They inherit their mechanical strengths from bulk carbide and nitride. They are also metallic, unlike great majority of other two-dimensional materials. Graphene is zero band gap semiconductors. Majority of material are true metals with a high density of states at the Fermi level. But they can be dispersed just in water, produced after that in textiles, printed inks circuits. And they also have very large array of very useful properties, which are also quite unique, or combination of those, very unique, no other materials offer. And we can control them in many different ways. For example, very recently in this paper published just like a couple of months ago, we showed that niobium carbide MXene, which is flat, not semiconducting, but if we scroll it into a scroll, it becomes superconductor. So we can control properties by controlling morphology of the material, for example, again, scrolling it, making it tube, by intercalating between the layers of MXene some molecules. Again, we can make it superconducting by changing surface chemistry. So those are truly designer materials. But moreover, they're very easy to work with. In conventional method, we take max phase, etch it, make something we call MXene clay, multi-layer, non-delaminated MXene. Delaminate in solution, and because of high negative potential on the surface, we can make a colloidal solution just in pure water. No additives needed to disperse it, and by controlling concentration and flake size, we can make inks for spray coating, inkjet printing, or spin coating, or we can make viscose MXene for doctor blading or for drawing fibers, colloidal solution of flakes, which becomes actually liquid crystalline. And what is interesting, right after processing, we can get very strong films in tension. You see, it can support a car. It has mechanical strength comparable to aluminum. And you will see my former student is removing 1 micrometer thin film, 50 times at least thinner than human hair, 10 times thinner than aluminum foil that people usually use in batteries, say electrodes. And it's sufficiently strong to handle. This is very, very unusual, produced just from water on the surface. Strong, conducting electronically. Imagine battery current collectors, other applications with these films. You can also process MXene into composites with polymer matrices and make very large number of composites. That's also very important because two-dimensional materials, nanoparticles, are very often used within composites. And of course, this is an example of polymer matrix. We wrote a review with my student, but you can use ceramic metal matrices as well. Now, where can we use those properties? First of all, for new materials, we always need to explore applications where they can outperform other materials. And this is actually a case for MXene. They can enable applications where no other material can work or do something much better, providing disruptive technologies. This is an updated plot from our article published on occasion of my European MRS award, Chokhralsky Prize, showing that there are numerous applications emerging. And you see, this is virtually started all 2016, 2017. So it means that it's maybe like an 8-9-year-old. For a new material, that's very little. But you see how accelerating it is. And different fields grow at different rates. For example, sensors have been one of the fastest growing segments. We discovered MXene working on battery materials, supercapacitors. And this field also keeps expanding. Different type of batteries, sodium-ion batteries, other batteries emerging, zinc, zinc metal, zinc ion, and others. But besides this main application being explored, there are many, many other applications. From infrared stealth to water desalination, to optoelectronics, to electrochemical actuation, antennas, and much, much more. So it's truly very promising because unique properties of MXene open opportunities for use. I will give just a couple of examples. In 2016, together with Korean collaborators, we published this first paper in Science showing that titanium carbide MXene aligns with metals, much more conducting, aluminum, copper, in ability to shield microwaves, electromagnetic waves, basically stop waves from penetration. And you remember I showed you 1 micrometer film? You cannot make 1 micron freestanding film of copper or aluminum, but you can make it at room temperature easily from water with titanium carbide. This paper has been cited now about 5,000 times, became the most cited paper in the entire field of electromagnetic interference shielding. And technology already licensed and sub-licensed by many companies for practical use. But we showed in 2020 that titanium carbonate at the same thickness can even outperform metals. We still don't fully understand the physics of the process, but it's quite exciting from standpoint of applications. These materials reflect the waves. But if we take another MXene, vanadium carbide MXene, put it in a polymer composite, we can make materials which absorbs electromagnetic waves, making, for example, invisible to radar material. The properties, shielding ability, depends on the composition. It's proportional to conductivity of materials, but there are deviations. And this is very interesting physics to explore. And of course, there are many interesting practical applications. We can use more or less the same property. Conductivity, ability to make thin metallic coating from solution for a different purpose, to transfer waves in waveguides. And particularly, it's important for satellites, but also for many other applications. Because waveguides are used everywhere, even in your microwave oven at home, where you warm up sandwiches, you have waveguides because they transfer microwaves to the purpose. Usually made of metals, expensive and heavy components. What we did, we made plastic waveguides printed, very cheap, no machining inside needed channel. And there many have complex shapes and bend and so on. They became 10 times lighter, coated nylon with MXene, 1 micrometer or less. And actually they're cheaper to manufacture than metal, even with MXene coating, because plastic is so inexpensive. So we can make nowadays material which is cheaper than metallic component and works equally well. And it already has been licensed to MXene Dynamics Corporation, which is moving it towards production. We can print antennas for 6G range, for other ranges, again, making similar radiation efficiency to copper antenna, but much thinner and much lighter, what is important, with actual excellent efficiency. So communication is very important field. We can make stretchable, so-known resonant surfaces, where frequency of communication will be changing, or shielding properties will change as we strain and stretch it. We can modify the performance over a very broad range of frequencies. So those are very important applications, but there are many others. For example, titanium carbide MXene is a very poor emitter of infrared radiation. What does it mean? That if you take a picture with an infrared camera of a 200 nanometer film that is on a glass slide on a template, it will hold, this is after 5 minutes, steady state, 40-degree radiation temperature compared to 120-degree hot plate background. 200 nanometer, almost transparent film. 3 micrometer film can have a 300 degrees temperature drop. For example, like making it invisible to infrared camera. This is my student took his white shorts, washed white shirt in MXene, and you see, originally it was showing temperature of the body almost. After MXene coating, it looks cold, blue, like background. So it means that it keeps someone warm in winter. One can make, for example, clothes for wearing on moon, where it's very cold or very hot, or Mars, and or make it invisible to infrared cameras, camouflage, and so on. But why it's also possible? Because unlike metals, which also don't emit an infrared, MXene also has very low thermal conductivity, below 1 watt-meter Kelvin. So we have thermal insulator and poor thermal emitter. Very, very important combination of properties. We can make transparent stretchable electronics, replacing indium tin oxide. So every cell phone, computer screen has indium tin oxide here on screens, transparent conductor. By replacing it with MXene, we can tune the work function to the light emitting die, for example, and we can have an increase by an order of magnitude in brightness and flexibility, because indium tin oxide cannot bend, it cracks the ceramic. Moreover, recently we published this paper in Nature just in January this year, showing that we can make stretchable up to 200% stretchability, because 2D flakes can slide relative to each other. We can make stretchable films of MXene. They made stretchable light-emitting dye and full color displays that can be weared and can bend, can stretch when put on our clothes, for example, things here. So those are new opportunities being opened by MXenes. There are many more. I won't be able to talk about all of them, but another one I feel is very important in bioelectronics, wearable sensing technology that allows monitor health continuously. And what is also important, in this case, MXenes have done something that no other material could do. Enormous increase in efficiency and stretchability of devices. In this case, there are other materials can do it. Currently, gold is used. This is a gold electrodes standard commercial. Those are lab-made. Look at how much spike intensity, sensitivity is higher in MXene compared to gold, because it has lower impedance with skin, so it replaces gold, making much less expensive electrodes. You cannot provide golden electrodes sensor to every person on the planet, but you can make it out of titanium carbide. We have enough titanium and carbon in the world, and it works better than gold. We can make electrodes, and again, technology has been licensed to a major international corporation for electromyography, muscle movement, electrocardiography, electroencephalography. Also, we can make implantable electrodes of MXene because of its biocompatibility for brain implants, for example, and brain stimulation. So there are many exciting applications which truly open new avenues. Just take a look at biomedical research and those data from a year ago, roughly. And this is where we actually work a lot with Ukrainian collaborator from Sumy State University, Maxim Pogorelov's group. He's himself in Latvia now, but keeps positions there, and there are excellent researchers there. We work on cancer therapy, photothermal therapy. We work on wound healing materials. We work on tissue engineering. We work on drug delivery, and we also work on sensing, biosensing, and neural interfaces, and more. For example, mass cytometry, which is a kind of sensing, I could say, or analysis, biochemical analysis here. So sky is the limit. I think I've used all my time and probably even more because we started late. Conclusions I want to leave with you with. Use MXenes as new materials where no other materials can work. Think big. MXene can make science fiction really possible. from spacesuits to humanoid robots to more. I did not take time to talk about it, but I did talk to school children in Ukraine just a month ago. And it was really fun to discuss how we can make science fiction reality with new materials. They really offer solution to problems other materials could not solve. We can design them as needed. And we should not use always titanium carbide MXene. It's not a single material. We really need to design material for application. And I think there are truly opportunities for using all the wonderful properties of this new family of materials and combine them with other two-dimensional materials to build this new materials world. Before I finish, there are at least 5 major MXene conferences this year. There will be special session, symposia at professional society meetings, but second Euro MXene conference in Dublin, just in a week. I will fly to Europe tonight. Another conference in Italy, and then conference in China, United States, South Korea. So it's really shaping into a very large material field. We can still accept posters for our conference on MXene, which will be in Chicago. My colleague Dmitry Talapin chairs it this year with several other colleagues. And you can still submit the paper. I think my presentation somehow crashed. Okay, let me get it back. Decided to close here. So there is also another conference. I know many of you have probably attended it, UCAMAT 2026. We always talk about MXene there. I will be presenting, and it's also still possible to submit your abstracts to UCAMAT and come to beautiful Herceg Novi in Montenegro in September. And finally, if you plan further, Maxim Pogorelov, together with my brother, Alex Gagotsi, and 2 of my former students, Professor Now and our collaborator, Lucia Delogu, will be organizing a MXene symposium at a Ukrainian international conference, NAP 27. It will be in Riga, in Latvia, in September 27. So you can plan in advance. There will be a MXene symposium there. So again, come learn about MXenes, join efforts, research efforts in this field. And this is my very last slide. Of course, all this work was not done by myself. Those result of efforts of large, interdisciplinary, international research group. We collaborate with many people. We collaborate with Carbon Ukraine. We collaborate with colleagues all over the world. And of course, thanks to many organizations for support. And definitely, thank you for inviting me. And I'm glad to have this opportunity to talk to you.
Thank you very much for this comprehensive overview of the work. I'd like to hear some questions from the audience. Questions, please.
So, you compared MXenes to aluminum in some aspects, but from the current application trends, MXenes seem to be developing primarily as functional materials rather than structural aerospace materials. So I have 2 questions. First one, do you think that is really to remain the case long term? And the second one, what main limitation currently preventing their broader aerospace application?
Look, I did not talk about a number of things. One of the reasons I can talk, we work with Air Force Research Laboratory in the United States, but I cannot really talk about this work. But let me just stress, they are truly functional materials, but they are strong materials. I showed you example of pure MXene film made of just larger MXene flakes like papier-mâché, and it already becomes very strong mechanically in tension. But there was a paper published by Chinese scientists in Science magazine a year ago showing strengths of 2 gigapascal where MXene is combined with graphene like as layers, and these layers are bonded by organic molecules. 2 gigapascals is strength of high strength steel, 2 times higher, stronger than regular steel. So what it means that you can assemble complete fuselage structure, but give it also other properties, such as electromagnetic interference shielding, stealth, and so on. There are papers on this, but also we need more material. We need to scale up production. For structural materials, we always need larger amounts. So it's possible, just need to make more material and work more on optimization of mechanical properties.
Please. One more question, please. No? Yuri, is any Ukrainian company commercializing your achievement in anti-radar technology today?
Andrei, cannot hear you very well, Andrei.
Okay, is any Ukrainian company commercializing your materials, your coatings in anti-radar systems?
Hello.
Can I ask a question?
Yeah, just a moment, Tatiana.
Yeah, I see Tatiana has a question online here. Look, at the moment, Carbon Ukraine produces on campus of Institute of Material Science MXenes. They also make max phases. We purchase them. They have a license from Drexel University. Now, this is still small-scale production because they make materials for research. Ukrainian companies can produce potentially much more material. One need to invest and build. So we are very much open. Drexel University offers licensing, and it's just a matter of building up. Properties have been shown, and one can produce MXenes in Ukraine because Alexei and his company have been producing MXenes for quite a while.
Thank you for this comment, Tatiana. Tatiana, please.
Thank you. I'm very grateful for Yuri for such excellent presentation, exciting presentation, and also some big variety of applications of MXenes. And my question connected with superconducting MXene niobium carbide. I would like to ask you whether amount of turns influence superconducting temperature, for example, and how affect functional groups of the surface of this material, also superconductivity. And maybe you know some theoretical explanation for this. Thank you.
Yeah, basically, good answer. Let me start from the end. Actually, chemically tunable superconductivity has been predicted for moly niobium carbide MXenes by Boris Jakobson. So there was a prediction. Then Dmitry Talapin from University of Chicago showed in 23 that niobium carbide with sulfur selenium terminations become superconducting at about 4 Kelvin. But with oxygen and OH, it was not superconducting, at least not down to 2 Kelvin. We showed this. This is a very recent result, just published a couple of months ago. We showed that scrolling with changes, it basically changes the electronic structure. Where we bend material strongly scroll, we change the electronic structure by stretching, straining bonds. Obviously, this is the reason. I have not seen people modeling how strain affects superconductivity. But people showed that strain in the lattice leads to, for example, even opening the band gap in material, or for semiconducting MXene moving from indirect to direct band gap. We did not study the number of turns or radius. This is to be done. Moreover, this measurement was still done on films of many scrolls. We need to do measurement on single scrolls to really answer your question. How many turns? What is the radius of curvature? How they affect superconductivity? But that's what is exciting about MXenes. We're just scratching the surface. There is so much both fundamental interest in science to do, but also develop application, develop scalable technology. And that's why it's very important that many people work on it. It's not like a task or a single lab.
Thank you very much.
Okay. Any question in the audience here? Any question from internet? Yuri, thank you very much once more for presenting.
I thank you again for giving me opportunity to speak. Щиро дякую. Мені було дуже приємно виступити з доповіддю сьогодні. Коли у вас є питання, надсилайте на електронну пошту, будь ласка. І я бажаю вам усього найкращого, цікавої конференції та також тижня без проблем, щоб усе було тихо та спокійно у Києві. І усі ми сподіваємося, що ця війна закінчиться у цьому році. Усього найкращого. До побачення. Goodbye. Have a wonderful conference. Enjoy science despite all the challenges, everything you are experiencing in Ukraine. I really respect everyone so much for continuing doing research despite the war. Thank you. Goodbye.
Дякую. Абсолютно. Будь ласка. Якщо немає, є